Something is awry in our expanding cosmos. Nearly a century ago, the astronomer Edwin Hubble discovered the balloon-like inflation of the universe and the accelerating rush of all galaxies away from each other. Following that expansion backward in time led to our current best understanding of how everything began: the Big Bang. But over the past decade, an alarming hole has been growing in this picture. Depending on where astronomers look, the rate of the universe's expansion, a value called the Hubble constant, varies significantly. Researchers hope that the James Webb Space Telescope, the most advanced telescope in history, launched in late 2021, would help to settle the question once and for all. But consensus has so far failed to materialize. Instead, a Nobel Prize-winning physicist from Johns Hopkins University says that new data collected by James Webb has just confirmed our understanding of the universe was completely wrong, and we may have to rewrite all the textbooks. Join us as we explore what's exactly going on. The most widely accepted explanation for the history of the universe has its beginning with a bang. Then, in an instant, the young cosmos was formed, an expanding, roiling plasma broth of matter and antimatter particles that popped into existence, only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma mire should have consumed each other entirely. But scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded contents stretched space-time, pulling a small fraction of this matter safely from the fray. As the universe inflated like a balloon, the standard story goes, ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies, connected together by a vast cosmic web. Initially, as the universe's content spread out, its energy density and therefore its expansion rate decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of space-time. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda-cold dark matter, or LCDM model of cosmology, which maps the growth of the cosmos and predicts its end, with matter eventually spread so thin it experiences a heat death called the Big Freeze. Many of the model's predictions have been proven to be highly accurate, but here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said, "Most people agree that the universe's present composition is 5% ordinary, atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is, we don't understand the last two of them." But an even greater threat to the LCDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. And methods that peer into the early universe show it expanding significantly faster than LCDM predicts. Those methods have been vetted and verified by countless observations. However, Measuring the universe's expansion takes a little bit more than a radar gun. The first method to measure this growth looks at the so-called cosmic microwave background, or CMB, a relic of the universe's first light, produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump. As the universe exploded outward, this soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter, and a value for the cosmological constant, or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megaparsec. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will retreat from us, and us from it, at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,140 kilometers per second and continues to grow exponentially there onward. If a galaxy is any further than 4,475 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables, dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant, standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. And in the words of Wendy Friedman, an astrophysicist at the University of Chicago, it's one of the most accurate means that astronomers have today for measuring distances. To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then, astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 kilometers per second per megaparsec when compared to the Planck measurement. The apparent paradox between the two measurements is what cosmologists have started calling the Hubble tension. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. One possible explanation is that there is a measurement error on the bottom rung of the cosmic distance ladder, which is home to the Cepheid variables. These are stars with luminosities that predictably fluctuate as the stars pulse in and out. The longer the pulsation period between moments of maximum luminosity, the greater that maximum luminosity is. This period luminosity relation allows us to accurately calculate their distances to Earth. It's possible to measure the pulsation period to calculate maximum luminosity. Then, based on how bright a Cepheid variable appears in the sky to us, we can work out how far away it must be to appear that bright. But it's not quite a foolproof method. The Hubble Space Telescope is able to observe Cepheid variables in distant galaxies, but the more distant they are, the harder they become to distinguish among all the other stars that crowd around them. As such, there was a concern that unresolved stars adjacent to Cepheid variables in these faraway galaxies were adding to the Cepheid's apparent brightness values, creating an unseen and systematic error in the measurements. Interstellar dust can also affect the brightness of Cepheid variables, dimming them from our vantage point on Earth. But new measurements achieved with the James Webb Space Telescope of 5 galaxies, hosting a combined total of more than 1,000 Cepheid variables, have ruled this possible error out. James Webb's infrared vision is able to cut through the interstellar dust, while its greater resolution allows it to clearly resolve the Cepheid variables so they stand out from the crowd. From these Webb's measurements, astronomers led by Adam Rees of Johns Hopkins University determined that Hubble's original measurements were spot on. The 5 galaxies, observed by James Webb, the most distant of which is NGC 5468 at 130 million light-years from us, have also hosted a combined total of 8 Type 1 supernovas over recent decades. These supernovas, which signal the destruction of white dwarfs, have a standardizable luminosity curve and form the next rung on the cosmic distance ladder above Cepheids. Because the preceding rung is required to calibrate the next rung, observations of Cepheid variables made by James Webb therefore makes the distance measurements using Type 1 supernovae, which are bright enough to be seen in much more distant galaxies than Cepheids, more accurate. And they too tell us that there is a contradiction in the different measurements of the Hubble constant. In other words, the tension at the heart of cosmology is here to stay. But with measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe. And we need to find out if we are missing something on how to connect the beginning of the universe and the present day. At that time, some scientists strongly believe that the best way to solve the problem is to look for new physics that may explain the discrepancy. Some astronomers believe that Earth resides near the center of a supervoid, a large region of less than average density, roughly 2 billion light-years in diameter. The presence of this supervoid would affect our measurements of the expansion rate, because galaxies within the supervoid generally flow outward toward the void's edges. So, when we go to measure how quickly the universe is expanding by looking at nearby supernovae, they get an extra speed boost because of this outward flow, which could possibly explain the tension. A team of researchers followed this line of thinking in a paper recently accepted for publication in the monthly notices of the Royal Astronomical Society. But the existence of the supervoid itself may stretch the bounds of what our standard cosmological models can provide. It might just be too big. So to explain the existence of the supervoid, researchers have turned to MOND, short for modified Newtonian dynamics. This is an alternative hypothesis of gravity originally proposed to explain the behavior of galaxies without needing dark matter. But MOND itself doesn't do a good job of explaining the properties of the largest structures in the universe, and so the researchers had to add another ingredient, a new kind of particle known as a sterile neutrino. Essentially, sterile neutrinos are a different kind of dark matter that can work with MOND to explain large structures in the universe, like the local supervoid, which is ironic considering that the whole point of MOND was to get rid of the need for dark matter. So by leaning on a giant supervoid in our local region of the universe, a new theory of gravity and a new species of dark matter could enable researchers to resolve the Hubble tension and explain a relatively new result. This could show that galaxies in the local universe appear to be flowing away from us faster than they should in standard cosmological models. It's an unproven but intriguing combination of thoughts, and we will likely have to add something to our understanding of the universe to eventually explain the Hubble tension. But it's easy to add complexity to a model in order to achieve a desired result, and have that complexity add more headaches. In this case, the goal is solving the Hubble tension, and this model does so, at least in a preliminary fashion. But it takes an awful lot of complexity to get there. Not all astronomers agree that the local supervoid exists. It's tough to assess the overall density of the universe at these kinds of scales. Not all astronomers agree that the existence of the supervoid breaks our standard understanding of cosmology. It may be perfectly reasonable without leaning on new physics. Not all astronomers agree that the presence of a supervoid would distort our measurements of the Hubble constant. Supernovae may be largely unaffected, and few astronomers believe that monde is a viable theory. In fact, the vast majority of astronomers and cosmologists don't believe that monde works at all, especially considering that it still requires introducing some form of dark matter to explain the variety of observed structures in the universe. The sterile neutrino idea required to make this model work is purely hypothetical. An intriguing idea for sure, but not yet on solid ground. And lastly, for this model to work, the Milky Way would have to sit near the center of the local supervoid, not out near the edges, which is a difficult coincidence to include in any viable cosmological idea. This research could lead somewhere fruitful and possibly generate an interesting idea that could resolve the Hubble tension. Currently, the conclusions are based on relatively simple models of the growth of structures in the universe, and the next step will be to implement this idea in a more faithful simulation. And, ultimately, the evidence will decide the issue. But in the meantime, let's shift back the attention to James Webb. Most recently, NASA has just celebrated 2 years since the James Webb Space Telescope started sending images back to Earth. The telescope launched on Christmas Day in 2021, but spent the first few months in space calibrating its instruments as it prepared to observe the cosmos in infrared light. On July 11, 2022, President Biden and Vice President Harris revealed the first image from the $10 billion telescope in a press conference from the White House. This image featured the galaxy cluster SMACS 0723 and became known as James Webb's first deep-field image. This reveal was followed a day later by a live NASA broadcast, which revealed 3 more stunning images from James Webb, the event marked by this new image release. The pictured objects shown to the public on July 12, 2022, included Stephan's Quintet, the cosmic cliffs of the Carina Nebula, and some supernova wreckage left behind by a dying star. These images were accompanied by data collected by the telescope from the atmosphere of the hot gas giant exoplanet WASP 96b. In the 2 years since then, James Webb has continued to deliver images of staggering beauty, while also providing scientists with data that has revolutionized our understanding of the cosmos. The observatory has spotted the most distant galaxies ever seen by humanity, some of which are so distant they existed when the 13.8 billion-year-old cosmos was just 300 million years old. The most powerful space telescope ever has also observed quasars powered by supermassive black holes that existed less than 1 billion years after the Big Bang. This has actually provided cosmologists with a massive problem in explaining how these titans grew so massive so quickly in the infant universe. The Webb telescope is adept at spotting light from galaxies that has had its wavelengths stretched by the expansion of the universe, as the light spent billions of years traveling the cosmos. That's why the telescope is so good at seeing early galaxies and quasars. However, astronomers didn't expect the space telescope to be so useful much closer to home, particularly in our solar system. That was just a nice surprise. Rather than being blinded by close objects, as astronomers feared it may be, the powerful space telescope has been able to image familiar solar system bodies like Jupiter in an incredible new light. As NASA Administrator Bill Nelson said in the statement, since President Biden and Vice President Harris unveiled the first image from the James Webb Space Telescope 2 years ago, Webb has continued to unlock the mysteries of the universe. With remarkable images from the corners of the cosmos, going back nearly to the beginning of time, James Webb's capabilities are shedding new light on our celestial surroundings and inspiring future generations of scientists, astronomers, and explorers. And now, to celebrate 2 years since the James Webb Space Telescope began sending images back to Earth, NASA has released yet another stunning image taken by the revolutionary Space Telescope. The second anniversary Webb image shows 2 interacting galaxies that make up a single object called ARP 142, which appears like a cosmic penguin with its cosmic egg. Fittingly, for a celebration of James Webb's 2 years of science results, the new image is a 2 for 2. ARP 142's penguin and egg scene comprises 2 interacting galaxies located around 326 million light-years from Earth in the constellation of Hydra. It has been observed before, but never in as much detail as this view from the telescope has allowed. In the new image, ARP 142 is seen in infrared light by the James Webb's NIRCam and MIRI. The penguin is a misshapen spiral galaxy called NGC 2936, while its egg is the galaxy NGC 2937. The 2 galaxies are separated by around 100,000 light-years, which is actually quite close in galactic terms. For example, the Milky Way galaxy and the Andromeda galaxy, its nearest neighbor, are around 2.5 million light-years apart. The ARP 142 interaction began between 25 million and 75 million years ago, when the 2 galaxies first swept past each other, disrupting the spiral shape of NGC 2936. As the interaction continues, further golden threads will be pulled from this cosmic penguin until the galaxies finally collide and merge. Within the penguin part of this duo, NGC 2936's galactic center gleams in the cosmic waterfowl's head as a bright, shining eye. The unwinding arms of gas, dust, and stars of NGC 2936 form the penguin's beak, head, back, and fanned-out tail. Like most spiral galaxies, NGC 2936 is rich in gas and dust, which is being pulled on by the egg half of the situation, NGC 2937. This causes regions of increased gas density in NGC 2936 that cause bursts of star formation. These regions can be seen in the beak, feathers, and tail of the penguin in Webb's image. The new stars are surrounded by orange smoke-like gas containing carbon-based molecules called polycyclic aromatic hydrocarbons, which the telescope has become adept at seeing. While the penguin tells a story of disruption and upheaval, the galaxy that represents its egg is relatively undisturbed. NGC 2937 is an elliptical galaxy that is packed with older stars than those of NGC 2936. This galaxy consists of less gas and dust than its companion, which means the interaction isn't triggering the same bouts of intense star formation. The fact that the penguin and its egg are relatively the same mass has prevented one galaxy from simply devouring the other. Of course, NASA couldn't throw a party for James Webb if only 2 galaxies rolled up. The galaxy PGC 1237172 is at the top right of the penguin and egg image. The blue swoop is an edge-on view of this young galaxy, which is packed with blue infant stars and is just 100 million light-years from Earth. PGC 1237172 also performs quite a neat party trick for the observatory. The blue edge-on galaxy disappears when the same region is seen in mid-infrared by MIRI. Sorry to spoil the illusion. This happens because MIRI is better at seeing mid-infrared light from older stars and dust, with this galaxy's copious young stars vanishing in those wavelengths of light. Making up the rest of the party are a multitude of other distant galaxies. Some are semi-hidden within the tail feathers of NGC 2936, while others shine faintly in the background. In other observation made by James Webb just a few days ago, astronomers have observed the dramatic dance between a supermassive black hole and 2 satellite galaxies. The observations could help scientists better understand how galaxies and supermassive black holes grew in the early universe. This particular supermassive black hole is feeding on surrounding matter and powering a bright quasar that is so distant that James Webb sees it as it was less than 1 billion years after the Big Bang. The quasar, designated PJ30821, is localized to an active galactic nucleus, or AGN, in a galaxy that is in the process of merging with two massive satellite galaxies. Not only did the team determine that the black hole has a mass equivalent to 2 billion suns, but they also found that both the quasar and the galaxies involved in this merger are highly evolved, a surprise considering they existed when the 13.8-year-old cosmos was just an infant. The merger of these three galaxies is likely to deliver to the supermassive black hole vast amounts of gas and dust, which will facilitate its growth and allow it to keep powering PJ30821. As team leader Roberto De Carli, a researcher at Italy's National Institute for Astrophysics, said in a statement, "Our study reveals that both the black holes at the center of high redshift early and distant quasars and the galaxies that host them undergo extremely efficient and tumultuous growth already in the first billion years of cosmic history, aided by the rich galactic environment in which these sources are formed." The data was collected in September 2022 by James Webb's NIR-SPEC instrument as part of the 1554 program, which aims to observe the merger between the galaxy hosting PJ30821 and two of its satellite galaxies. De Carli added that the work represented a real, emotional roller coaster for the team, which developed innovative solutions to overcome the initial difficulties in data reduction and produce images with an uncertainty of less than 1% per pixel. Quasars are born when supermassive black holes, with masses millions or billions of times that of the Sun that sit at the heart of galaxies, are surrounded by a wealth of gas and dust. This matter forms a flattened cloud called an accretion disk that swirls around the black hole and gradually feeds it. The immense gravitational forces of the black hole generate powerful tidal forces in this accretion disk, which heat this gas and dust temperatures as great as 120,000 degrees Fahrenheit, or 67,000 degrees Celsius. This causes the accretion disk to emit light across the electromagnetic spectrum. This emission can often be brighter than the combined light of every star in the surrounding galaxy, making quasars like PJ30821 some of the brightest objects in the cosmos. While black holes don't have characteristics that can be used to determine how evolved they are, their accretion disks, and thus quasars, do. In fact, galaxies can be aged in the same way. The early universe was filled with hydrogen, the lightest and simplest element, and a little helium. This formed the basis of the first stars and galaxies, but during the life of these stellar bodies, they forged elements heavier than hydrogen and helium, which astronomers call metals. When these stars ended their lives in massive supernova explosions, these metals were dispersed throughout their galaxies and went on to be the building blocks of the next generation of stars. This process saw stars, and through them galaxies, becoming progressively metal-rich. The team found that, like most AGNs, the active heart of PJ30821 is metal-rich, and the gates around it are being photoionized. This is the process by which particles of light, called photons, provide the energy that electrons need to escape atoms, creating electrically charged ions. Now, one of the galaxies that's merging with the host galaxy PJ30821 is also metal-rich, and its matter is also being partially photoionized by electromagnetic radiation from the quasar. Photoionization is also happening in the second satellite galaxy, but in that case it is being caused by a bout of rapid star formation. This second galaxy also differs from the first and the AGN, as it appears to be metal-poor. According to team member and astrophysicist Federica Loiacono, thanks to NIR-SPEC, for the first time we can study, in the PJ30821 system, the optical band rich in precious diagnostic data on the properties of the gas near the black hole in the galaxy hosting the quasar and in the surrounding galaxies. We can see, for example, the emission of hydrogen atoms, and compare it with that of the chemical elements produced by the stars to establish how rich the gas is in metals. Though light leaves this early universe quasar across the broad range of the electromagnetic spectrum, including optical light and X-rays, the only way to observe it is in infrared. That's because, as the light has traveled for over 12 billion years to reach James Webb, the expansion of the universe has stretched its wavelengths considerably. That shifts the light in the direction of the red end of the electromagnetic spectrum, a phenomenon understandably called redshift, which is denoted as Z by astronomers. James Webb is adept at seeing high redshift or high Z objects and events like PJ 30821 because of its sensitivity to infrared light. In other words, thanks to the sensitivity of James Webb in the near and mid-infrared, it was possible to study the spectrum of the quasar and companion galaxies with unprecedented precision in the distant universe. Only the excellent view offered by James Webb is able to ensure these observations. Elsewhere, a sparkling jeweled ring, created through a cosmic phenomenon called gravitational lensing, has been imaged by the James Webb Space Telescope. The new image captures a distant quasar known as RxJ1131-1231, which lies about 6 billion light-years from Earth. The powerful gravitational field of a nearby elliptical galaxy, located in the foreground of the image, warps the light of the quasar, which is an extremely luminous AGN, creating a bright arc and duplicate views of the object, ultimately procuring a visual that looks like gemstones on a ring. The elliptical galaxy creating the gravitational lens in the new James Webb's image appears as a small blue dot in the center of the ring. The galaxy acts as a natural telescope, magnifying the light from the more distant quasar, which is otherwise too far away to study. The new image was taken using James Webb's MIRI as part of a larger study of dark matter and its distribution in the universe. With these recent observations and previous views from other telescopes, RxJ1131-1231 is considered one of the best lensed quasars discovered to date. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.